Hello, my name is Joel Steinberg. I am a physician certified in psychiatry and two other specialties. Although I am on the teaching faculty at Case Western Reserve University, I have had no experience in teaching in public schools. I did attend public schools. As a psychiatrist, I have had a major interest in the nature of consciousness and the tools used for cognition. This is an old interest. I have been working on the system called Funforms that I am about to explain to you for the past 20 years. It all began with a friend and colleague who is now dead. Thinking takes place with pictures and symbols. Animals, of course, don't have many symbols. Human thinking, particularly after age 5 or 6, takes place primarily in words and numbers. It is also interesting to note that to some extent the quality of the symbols used has something to do with the capacity to think. For example, some indigenous tribes can only count to 3 or to 4. Other indigenous tribes, by naming parts of the body, were and are able to count as high as the low 30s, but none of these people had significant computational capacities. Some of these indigenous peoples still exist. When they are taught our numerical system, Hindu-Arabic numbers, they become numerically empowered. You see, numbers can either be representational and or computational. For example, Roman numerals are primarily representational. Roman numerals are not very useful for computation. People who used Roman numerals had to use an abacus or some other means for doing computation. Then they recorded the results in Roman numerals for a permanent record. It seems obvious that numbers are more useful when they are both representational and computational. Hindu-Arabic numbers are both representational and computational. However, our number system is arbitrary in design, and that alone can make learning our system an obstacle. Also, after learning the various symbols that we use, a lot of additional memorization is necessary. For example, sums and multiplication tables. This can make learning our number system difficult. The system that I am about to explain to you is ultimately simple in design. I think you will agree that it is stark, but the individual ciphers or glyphs, by that I mean the individual numbers themselves, are iconic and ideographic. They are easily learned and easily written. When they are used for computation, operations become transparent. Understanding of many aspects of our numbers is facilitated. The continuity between fractions and whole numbers is particularly made obvious, and the relationship between positive and negative numbers is also made obvious. As I mentioned, Funforms is the name of this system. Fun stands for fundamental, for functional, and for fun. Forms stands for formulae. Funforms are fundamental, functional formulae that are fun to work with. So, now you are about to learn about Funforms. I think it is the first advance in the general written numbering system in 1,000 years or more. My goals today are to teach you enough about Funforms that you will either choose to teach yourself everything else, or you will contact me for further instructions. A CD containing the entire lecture and other written materials is available upon request. The entire PowerPoint slideshow can be downloaded from the website funforms.com. Eventually, my goal is to have Funforms introduced into the public school curriculum, probably at the middle school level. I believe that gifted students will experience enriched learning as a result of learning Funforms and seeing how it works. I think Funforms is a second language for mathematics, and in the same way that learning a second language enhances your understanding of your own language, learning Funforms will enhance a student's understanding of our math system. It is possible that students with dyscalculia may benefit from learning Funforms. If that is so, it probably would have to take place at an earlier time in their lives than middle school. You could easily ask, well, don't we already teach an alternate numbering system in school? Well, the answer is yes. We have already alluded to Roman numerals. We teach Roman numerals in most classrooms. Everyone knows what this figure means, don't they? It means 6. Yes, everyone knows what 16 means. XVI. It means 16. The problem is that Roman numerals are not easily manipulated. That is to say, they cannot be used for computational purposes. A student learning them learns little or nothing about the facts about how numbers work. By how numbers work, I refer to the computational aspects of using numbers for various operations. Funforms is a numbering system that is easily manipulated. It is a tally mark place order binary system. As I said to you earlier, to the best of my knowledge, it is the first one. All of you recognize what this figure means. It is 3 groups of 5 tally marks and 1 extra tally mark. It means 16. It means 16 just like the Roman numeral that we just saw. Tally marks were probably the first counting system. Primitives probably simply counted by using corresponding tally marks. That is to say, 1 tally mark stood for 1 sheep, or something like that. It enabled people to know how large a collection was and to keep a record of the collection. That way they could recognize if a member was missing. However, whether it was truly counting or not is something that could be argued. My opinion is that it is a pre-counting precursor system, but I don't want to argue about it. It is a pragmatic issue, a matter of definition alone. Using tally marks 1 for 1 is certainly not sophisticated counting, but it is a lot better than nothing at all. How about if we wrote 16 vertically like this, or if we wrote it vertically but like this? You would still recognize and understand that it represented the number value 16, wouldn't you? Well, that brings us to Funforms. In Funforms, the glyphs, which could also be called ciphers or numerals, are written vertically, as you see here. There are specific positions where a horizontal mark can be written. I refer to the horizontal marks as flags or as tally marks. The flags reside on a vertical structure called a staff. The staff has no value of its own. It is there simply to provide a structure on which to write the tally marks. That helps keep them coherent and part of one figure. I have found the best way to write Funforms is on lined notebook paper, just like what students use in school. Then one can just drop a vertical line, the staff, and wherever there are lines on the paper are the only places where a tally mark can be written. Although it is beyond the scope of this particular discussion, and beyond what I have actually explored, I have at least considered the possibility of using intermediate places on the staff to represent numbers like pi or e. Also, square roots, cube roots, and other irrational numbers might also be written between the lines. I have not considered these issues sufficiently to discuss them. I leave that development of Funforms to others. I have also considered the possibility of a three-dimensional structure wherein imaginary numbers might be written perpendicular to the plane of ordinary positive and negative numbers. Number values double at each successive position going down the staff. To be consistent, I started this slide at 16. It is written at the 5th position going down the staff. Positions following 16 are 32, 64, 128, and 256, as you see here. Ascending the staff, number values halve, as can be seen in the balance of the slide, 8, 4, 2, and 1. There are a few additional things that you will need to know to actually be able to use Funforms. Positive values are drawn to the right of the staff. Negative values are drawn to the left of the staff. When a positive and an equivalent negative tally mark are at the same point on the staff, they intuitively can be seen to cancel one another out. Ordinarily, when we write our own numbers, we do not need to put in a decimal point. The decimal point is simply understood. We only write the decimal point if there is to be a decimal portion to the number. This convention is followed in Funforms as well. Ordinarily, the first position is where the number 1 would be written if it were part of that particular Funforms numeral. Sometimes, though, we need to write fractions or mixed numbers, and then we have to designate where 1 would be. I call that position unity point. Recall that a moment ago you learned that number values doubled in value as tally marks go down the staff at each successive position. And you learned that number values halve as they go up the staff. All potential positions below unity point have a whole number value that corresponds to a whole number power of 2. As you see demonstrated here, 1 is at 2 to the 0, and the exponents of 2 proceed arithmetically at each position going down the staff. All potential positions or points above unity point are fractional in nature and represent the value of whole numbers of 2. As you see here, the first position above unity point is 2 to the minus 1, then 2 to the minus 2, and so on. These have a value of 1/2, 1/4, 1/8, and so on. I want to tell you a little bit more about pairs before we start counting. Most people that I talk to about Funforms believe that people started counting by tens because there are 10 digits on our hand and 10 digits on our feet. But I say we probably started counting by pairs. I say that first because 2 is the simplest number concept beyond 1. And second, I say that because we are bilaterally symmetrical and there are paired organs on both sides, like 2 hands and 2 feet. So from my point of view, the first counting number after 1 is clearly 2. Whether the first person who came to realize that used the same concept next to consider a pair of pairs, or he considered a pair plus 1, is lost in history. In Funforms, though, the next simple point is a pair of pairs, and following that comes a pair of pairs paired. With that little detour, now I would like to begin counting. If we put a flag at the first potential point, we have 1. A flag at the second position is 2. A flag at both of these positions represents 2 and 1, or 3. 4 is a flag at the next potential space down. 5 is simply 4 and 1. Here starts a repeating pattern. I want to call your attention to the fact that each odd number has a flag at the top space. Each even number is missing a flag at that space. The pattern now will repeat itself. At 6, we see 4 and 2. At 7, 4, 2, and 1. There is no place to put another flag. This is what I call full. The next tally mark goes at the next space down. That's 8. The next number will be made up of an 8 and a 1. 9 is 8 and 1. 10 is 8 and 2. 11, 8, 2, and 1. 12, 8, and 4. 13, 8, 4, and 1. 14, 8, 4, and 2. Note that 14 looks exactly like 7 did, except all 3 flags have been moved down 1 space. That is to say, larger numbers also double in value when they are moved down 1 space, and halve when they are moved up 1 space. 15 is 8 for 2 and 1, and again we have a full staff. There is no room for another tally mark. The next tally will be at the next space down. There is 16. After 16 comes 16 and 1, then 16 and 2, then 16, 2 and 1 makes 19, 16 and 4 make 20. Now, it is valuable for people to learn to write the numbers on their own. If this is the first time you are learning Funforms, I suggest you stop for a moment and try to write all of the numbers up to 20, or try to write the numbers from 20 to 40. Let's go on now to the rules that are necessary to manipulate Funforms. I remind you that numerical values double each time a flag or a series of flags move down one position or a set of positions on. Similarly, and for the same reason, numerical values halve each time a flag or a series of flags moves up one position or set of positions on. Another rule you should keep in mind is that no more than one flag can be at any one position except temporarily during manipulation. That is to say, in a final figure there is either one flag at any given point or position, or there is no flag at that point or position. Here is our first simple addition problem. I have shown you 3 made up of 2 and 1 with red tally marks, and 5 made up of 4 and 1 with yellow tally marks. To add them, they are simply combined or coalesce. Once they are all on one staff, the tally marks are cleared by using the rules you have already learned. Any 2 tally marks at one position are the same as 1 tally mark at the next position down. Here you see the 2 red flags combined with the 2 yellow flags. And here they are made more plainly visible. There are 2 tally marks at the 1 position. That is the same as 1 tally mark at the 2 position. And although I don't want you to think about it this way, 2 1s make a 2. So those 2 tally marks become 1 tally mark at the next position down. But there already was a tally mark at that position. Now there are 2 tally marks there. Those 2 tally marks are the same as 1 tally mark at the next position down. And although I do not want you to think about it this way anymore, 2 2s are the same as 1 4. And so, when we move those 2 tally marks down, we encounter the same problem. Now there are 2 tally marks at that position. And again, although I do not want you to think about it this way, 2 4s are the same as 1 8. Any 2 tally marks at one position are always the same as 1 tally mark at the next position down. So, here we have the final figure, 1 tally mark at the 8 position. 3 and 5 make 8. We have done it totally mechanically, however, simply coalescing the 2 figures and then clearing it by the rule, whenever there are 2 tally marks at one space, they are the equivalent of 1 tally mark at the next space down. Let's turn to a little more difficult addition problem. Here I have shown you 65 in red, made up of a tally mark at 64 and at 1, and 91 made up of a tally mark at 64, 16, 8, 2, and 1. 64 and 16 are 80, and 8 make 88, 2 and 1 make 91. To add these figures, we simply coalesce them, as you see here. Now, what happens to the 2 bottom tally marks is they simply move down to become 1 tally mark at the next space down. And although I do not want you to think about it this way, I will mention for the last time that 2 64s are the same as 1 128. The 2 tally marks at the 1 position become 1 tally mark at the next space down, as you see in the next step of solving this problem. Now there is only one place where there are 2 tally marks. Those 2 tally marks become 1 tally mark at the next space down, as you see here. The final figure then is 128 and 16, that's 144, and 8, 152, and 4, 156. This funform is now in its simplest form, and nothing further needs to be done or can be done. This is the answer even if you don't translate it back into Hindu-Arabic numbers. That is to say, if I spoke to you in a language that you didn't understand, what I would say could still have meaning, just it might not have meaning to you. So the 156 term is necessary for us to understand it, because Hindu-Arabic numbers are our number language, but the answer was there before we translated it back. Now, subtraction is very similar to addition. One simply converts the number to be subtracted to its negative counterpart by drawing the mirror image of it, so that flags that extended to the right now extend to the left. After that, the 2 figures are simply coalesced. Before we complete your education about this matter, I would like to show you what I call the zipper phenomena, or the Jacob's ladder phenomenon. Here is 16 take away 1. The 1 is converted to its negative counterpart, and the figures are coalesced. The 1 red tally mark is the same as 2 tally marks at 1 space up. One of those tally marks is the same as 2 tally marks 1 additional space up, as shown here. One of those 2 tally marks is the same as 2 tally marks at the next space up. Sliding the whole figure over, one of those 2 tally marks can be moved up 1 space, making 2 tally marks at that space. At that space, there is a negative tally mark to cancel one of those tally marks, and the resulting figure is these 4 tally marks that you see here. These are 8, 4, 2, and 1, which add up to be 15. But the larger point is that regardless of how large an intervening space is between a lower tally mark and an upper negative tally mark, the outcome will be that every single space, including the space of the negative tally mark, will be filled with a single tally mark beginning one space up from the original positive tally mark. You don't have to do it each time to know that that's how it works. It is the same as 10,000 minus 1, leaving 9,999. 16 minus 1 is Now, let's do a little more difficult subtraction problem. Here, shown with red tally marks, is 225, made up of 128 and 64, 192 and 32, 224 and 1, 225. Take away 44, made up of 32, 8 and 4. I don't want you to think about the Hindu Arabic numbers. It's simply the figure on the left, take away the figure on the right. We convert the figure on the right to its negative counterpart. We coalesce the figures, as you see there. The offsetting tally marks cancel one another, as you see here. Then, because of the long space between that lower positive tally mark and the first negative tally mark, that tally mark will have to be moved up, just like we did a moment ago when we took 1 away from 16. It makes 2 tally marks 1 space up. One of those tally marks makes 2 tally marks 1 space up. And one of those tally marks makes 2 tally marks 1 space up. The offsetting tally marks cancel, leaving just 1 tally mark at that space. That 1 tally mark has to move up 1 space, where it becomes 2 tally marks. There is an offsetting tally mark, which cancels one of those, leaving the figure that you see here. This figure is the answer to that subtraction problem. It can be translated back to Hindu Arabic numbers so that you will understand what value it actually has. It is 128 and 32, that's 160, and 16, 176, and 4, 181, 181. 225, take away 44, is 181. So I remind you again about 16 take away 1. Again, I think of this like unzipping a zipper, or like when you add 1 to 15, like a Jacob's ladder, with a mechanically tumbling down of the tally marks to the next space down. 15 plus 1 makes 16, as you see here. Now let's talk about multiplication. Multiplication really amounts to serial addition. It is done by writing the multiplicand at each position that a flag exists on the multiplier. Here we see the formulaic qualities of Funforms applied. Once each flag in the multiplier has been represented, the intervening figures are coalesced into one glyph, and that glyph is cleared of duplicate tally marks by the rules you have already learned. So on the left you see 6 made up of 4 and 2, turquoise and red tally marks respectively, and 10 on the right made up of yellow tally marks at 8 and 2. It is helpful to think of the 10 as space flag, beginning at unity point, as you see depicted here. Space flag will have to be written down first at the level of the red tally mark and then at the level of the turquoise tally mark to get the answer to this. Here you see the level of the red tally mark outlined, and here you see space flag being written at that level. It is written in red so that you can relate it back to that particular phase of the problem. What we have really done here is multiply 2 times 10. Notice that the answer is 16 and 4, which is 20. Next, we will have to write 10 down at the turquoise tally mark. As you see here, we will have to write space flag at the level designated there. To keep matters straight, I have represented the resultant figure in turquoise. This figure really represents 4 times 10, and if you notice, the result is 32 and 8, or 40, 4 times 10. So we have multiplied 2 times 10 and 4 times 10. That is 6 times 10. Now we are going to put those figures together, as you see here. All on one staff. That is the answer to the problem that we had, and we can translate it back just to check on it. 32 and 16 are 48, and 8, 56, and 4, 60. 6 times 10 is 60. Sometimes things change. Here are 2 dolphins. One of them slowly changing into a cow before your eyes. Here is a little more difficult multiplication problem. 22, represented by a green flag at 16, a blue flag or turquoise flag at 4, and a red flag at 2, times 6, made up of 4 and 2. 6 could be thought of as space flag. The task then will be to write space flag at the red tally mark, then at the blue or turquoise tally mark, and then at the green tally mark. We will have 3 intermediate glyphs that have to be coalesced, and then we will have to clear them. So the red tally mark is flashing. Here is the reminder. There goes space flag, and it is in red just so that you will know where it came from. This is 2 times 6, and in fact it shows that it is 8 and 4. Next, we will have to write space flag down at the blue or turquoise tally mark as you see here. Color-coded again for simplicity's sake. That is the result of 4 times 6, and notice that it is 16 and 8, or 24. Lastly, we have to write space flag down at the green tally mark level, as you see here. Next, these 3 glyphs have to be combined or coalesced, as you see here. Note that there are 2 tally marks at one level. Those 2 tally marks, in the same way that 15 and 1 made 16, will tumble down and become 1 tally mark at the 128 level. We could go through it though. 2 tally marks at the 8 level are the same as 1 tally mark at the 16 level. That makes 2 tally marks there. Those 2 tally marks become 1 tally mark at the 32 level, but there was 1 tally mark there. The 2 tally marks there become 1 tally mark at the 64 level. Those 2 tally marks become 1 tally mark at the 128 level. The answer to 22 times 6 is 128 and 4, or 132, as you see here. Again, I point out to you that the answer did not need to be translated back to be correct. We translated it back so that you would know that it is correct. What about fractions? I want you to consider this Funforms figure. It is 24, made up of 16 and 8. I want to point out that if you moved the 16 tally mark up to the 8 position, you would have 3 tally marks at the 8 position, and 3 eighths are 24, just as 16 and 8 make 24. If we move the figure up 1 space, it is halved. Half of 24 is 12. 8 and 4 is 12. If we move the tally mark at 8 up to the 4 space, it would make 2 more tally marks at that space for a total of 3. And so 4, that would make 3 of 4, or 12. Moving these tally marks up 1 space more, we have the value again. Half of 12 is 6. 4 and 2 make 6. The tally mark at 4 is the same as 2 tally marks at the 2 position. That would make 3 tally marks at the 2 position. 3 2s are 6. If we move the figure up 1 more space, we have a standard 3, or 3 of 1. By moving it up 1 additional space, it becomes fractional because we are passing unity point. Half of 3 is 3 halves, or 1 1/2. If we move the tally mark at the 1 position up 1 space, it would make 2 more at that space, and you would see that it makes 3 halves. By moving it up 1 more space, we have halved it again, and it makes 3/4. I did not draw the next halving procedure, but if we halved it 1 more time by moving it up 1 more space, it would be 3 of 2 to the minus 3. It would be 3/8. The same is true about fiveness or any other quantity written at any position. Here is 5 made up of 4 and 1. If we moved the tally mark at 4 up one space, it would make 2 tally marks at the 2 space. If we moved each of those tally marks up one space, we would have 4 more tally marks at the 1 space, and we would have 5 ones. This makes 5. If we move it down a space, it becomes twice that, or 10. 8 and 2 are 10. Or you could think of it as 5 of 2. By moving it down 2 more spaces, we have doubled it twice, and we have 32 and 8, or 40. If we had only moved it down one space, it would have been 20. Now, if we move 5 up above the unity point by moving it one space up, it becomes 5 halves, or 2 and a half, or 5 of 2 to the minus 1. Moving it up one more space, we have 5 fourths, or 5 of 2 to the minus 2. If we halved it yet again by moving it up one more space, we would have 5 of 2 to the minus 3, or 5/8. Well, I have good news for you. Adding fractions is exactly the same as adding any other Funform figures. You simply coalesce them, and wherever there are 2 tally marks, they become the same as 1 tally mark at the next space down. Here is 5/8 made up of red tally marks at the 1/2 and 1/8 mark, and 3/4 made up of a tally mark, yellow tally marks at the 1/2 and the 1/4 mark. I point out again that if we move the 1/2 tally mark up one space, it would make 2 more tally marks at that space. That would be 3/4. We do not need to seek a lowest common denominator. All we do is put them together. As you see here. The 2 tally marks at the lowest position will become 1 tally mark at the next position. Here is the answer. 1 1/4 and 1/8. That's 1 3/8. If you wonder about 3/8, just imagine moving the tally mark at 1/4 up one space. It would make 2 more tally marks at the 1/8 position. You would have 3 at that position, or 3/8. This is 1 3/8. Here is another adding fractions problem solved. 7/8 on the left, made up of the figure you are familiar with that looks like 7, 1/2, 1/4, and 1/8, and 1 1/2 made up of the red tally marks at the 1 and at the 1/2 position. To add them, we simply coalesce the figure, as you see happening here, and then the 2 tally marks at that one position become 1 tally mark at the next down, and those 2 tally marks become 1 tally mark at the next position down. And there is the answer, 2 1/4 and 1/8, 2 3/8. Again, I remind you that You can move the 1/4 up if you have doubts. It becomes 2 tally marks, 1 space further up, making 3 at that level. 7/8 and 1½ make 2 and 3/8. Adding fractions is delightfully simple in Funforms. Multiplying fractions is done just like multiplying whole numbers. You have to attend a little more carefully to how the flags on the multiplicand relate to unity point. Here we have 1/2 times 1/2. The 1/2 to be multiplied, reading from unity point going up, reads space flag, as you see depicted here. The task will be to write space flag at the position of the multiplying glyph. So we will make a temporary unity point at the multiplying tally mark, just as we did before. There is the new temporary unity point. The task will be to write space flag at that point, as you see happening here. 1/2 times 1/2 is 1/4, as you see depicted in the final figure. Now, on the left, we have 3/4 made up of a blue or turquoise tally mark at the 1/4 mark and a red tally mark at the 1/2 mark, to be multiplied times 3/4, made up of 2 yellow tally marks. If we read the multiplicand beginning at unity point, you would describe it as space flag flag, as you see depicted here. The task will be to write space flag flag first at the red tally mark and then at the turquoise tally mark. Here the red tally mark is identifying itself. Here is the line that we will need to write space flag flag at. There it is being entered, and it will be written in red to show you that that is what it is related to. Next, we will have to write space flag flag at the turquoise tally mark, which you see blinking here. There is the line that space flag flag will need to be written at. Here it is being written in turquoise. Now the task is to coalesce these figures and then to clear them. Here they are, coalescing. The 2 tally marks at the 1 position will tumble down to make 1 tally mark at the position, the bottom tally mark, as you see here. This figure is 1/2 and 1/16, or 9/16. 3/4 times 3/4 is 9/16. I am less happy about division than about any of the other operations, but division should be thought of as serial subtraction while keeping score. I believe that a student should be told that the task is to find out how many times a number can be subtracted from a given number. And here is an example of how I would explain that. Instead of saying 16 divided by 4, I would ask a learner, how many times can 4 be subtracted from 16? With the first subtraction, we are left with 12, and it has been subtracted one time. With the next subtraction, we are left with 8, and it has been subtracted twice. With the next subtraction, we are left with 4, and it has been subtracted 3 times. On the last subtraction, we are left with 0, and it has been subtracted 4 times. 16 divided by is 4. The same thing is done with Funforms. One has to keep score with how many times the number doing the dividing is subtracted from the number being divided. Here we see 35 divided by 7. 7 can be converted into its negative counterpart by simply writing it to the left. Then the first subtraction can be anywhere one chooses to make it. 7 is flag, flag, flag. In this case, we see flag, flag, flag move down 2 spaces to be subtracted. We have to keep track of those 2 spaces, which you see happening off to the right. There is where unity point was before we moved it down the 2 spaces. This is where we will record it. Now we have to do the subtraction. The turquoise tally mark will have to move up tally marks at the next space up. One of those gets canceled. That leaves 1 tally mark at that space. That tally mark has to move up a space where it will become 2 tally marks. One of those will be canceled, leaving 1 tally mark at the space. That tally mark has to move up 1 space, becoming 2 tally marks, and one of those will be canceled, leaving 1 tally mark at that space. Now it is time again to see how many times we can subtract 7 from the current remainder. We reverse the 7. We slide it straight across as you see there. We record that on our recording staff. Carry out the subtraction. Nothing is left. And we have subtracted 7 a total of 4 and 1 time, or 5 times. 35 divided by 7 is 5. Here is a different subtraction problem. In this case, I have not chosen to take the largest piece away first. We have 63 made up of tally marks at every number except 64. That is the number immediately preceding 64. And you can tell that because if you added 1 to it, it would tumble down and make a single tally mark at the next space down. Or you can add it up if you like. We convert 9 to its negative figure. It reads flag, space, space, flag. And we subtract it from the number to be divided. We have to record that first. We did not move it down any spaces. We simply are subtracting it. So a tally mark goes at the first position on the recording staff, as you see here. Then we carry out the subtraction. The opposing tally marks cancel one another, as you see here. Now, we have taken our flag, space, space, flag down 2 spaces to subtract it again, and we will have to record that on the recording staff. There is flag, space, space, flag written in red in the middle figure, and a tally mark has to be written on the recording figure. The subtraction takes place. The opposing tally marks simply cancel one another, and we are left with this figure. Flag, space, space, flag is now written in blue. It has been moved one space, and that has to be recorded on our recording figure, as you see here. Then the subtraction takes place. There is nothing left. The results of 63 divided by 9 are 4, 2, and 1, or 7. 63 divided by 9 is 7, and here we see that depicted. Dividing fractions is the same as dividing whole number. It is just serial subtraction while keeping score. Here you see on the left 5 1/2 to be divided by 2 1/2. We convert 2 1/2 to its negative number and slide it down 1 space, as you see here. Flag, space, flag. Unity point was in the middle. Unity point goes through the middle of the 2 red tally marks, as you see depicted here, and gets recorded here. When the subtraction takes place, the opposing tally marks cancel one another, and 1 flag is left. That remainder, and the results of the division is 2. 2 remainder 1/2. Here we have 25 made up of 16, 8, and 1 to be divided by 2 1/2. The operation is the same. 2 1/2 shows a tally mark on each side of unity point. We convert it to its negative form. It reads flag, space, flag, the space being unity point. We slide it down and keep track of where unity point was. We record that position as the first subtraction on the recorder staff and carry out the subtraction. The tally marks at the lowest position cancel one another. The tally mark above that position has to become 2 tally marks at the next position up. One of those is canceled by the opposing tally mark, and we are left with this figure. We take the flag space flag to this figure, moving it down 1 space, and record that on the recording staff. When we subtract those opposing tally marks, nothing is left, and on the recording staff we have tally marks at the 8 and at the 2 position, making 10. 25 divided by 2.5. Now sometimes people ask me how to make a Funform figure out of a Hindu Arabic number. The answer is relatively simple, and I have depicted it on this slide here. If the number is 96, we do a series of halving of the numbers, and every time an even number is left, no tally mark is written. Whenever an odd number is left, a tally mark is written, and numbers like 1/2 are discarded. So first we inspect 96, it's even. No tally mark is written at that space. I have put a dot to the left to indicate that there is a position there, but no tally mark. Half of 96 is 48. That's an even number. There is a dot written at that position. Half of 48 is 24. That's an even number, so there is a dot written at that position. Half of 24 is 12, so there is a dot written at that position. Half of 12 is 6, so there is a dot written at that position. That's also an even number. Half of 6 is 3, and that is an odd number. It gets a tally mark. Half of 3 is 1.5. We throw away the half. It is an odd number. It gets a tally mark. Now, looking on the right side, there was no tally mark at the 1, at the 2, at the 4, at the 8, or at the 16 position. There is a tally mark at the 32 position and at the 64 position. 64 and 32 make 96. Here is 87 done the same way. 87 is odd to start with. It gets a tally mark. Half of 87 is 43.5. We throw away the half. It is an odd number. It gets a tally mark. Half of 43 is 21.5. We throw away the half. 21 is an odd number. It gets a tally mark. Half of 21 is 10.5. We throw away the half. That's an even number. It does not get a tally mark. Half of 10 is 5. That is an odd number. It gets a tally mark. Half of 5 is 2.5. We throw away the half. 2 is an even number. It does not get a tally mark. Half of 2 is 1. That's an odd number. It gets a tally mark. So we have tally marks at 1, 2, 4, 16, and 64. 64 and 16 are 80. 4, 2, and 1 make 7. 87. That's the end. I hope you have enjoyed the presentation. If you have questions, I am available by email at joxl@sbcglobal.net. You can navigate back to any page you might choose to in the Funform presentation, You can also download the presentation without the narration if you choose to. That's the end. Thank you for your attention.